Hello, so today we'll be going over cell respiration, and this is the conversion of glucose into usable energy in the form of ATP. And as we go through all these steps, we're making these important byproducts such as NADH, FADH2 in order to feed into this formation of ATP. So to start things off, we'll actually begin with glycolysis. So glycolysis is when we take glucose and we make two pyruvate molecules. And as we go through this, starting off with the first step, we convert glucose into glucose 6-phosphate. This, with the help of hexokinase, will phosphorylate glucose, and doing so requires the use of ATP. And as we continue, we go from glucose 6-phosphate fructose 6-phosphate into fructose 1,6-bisphosphate. And with the help of phosphofructokinase 1, we phosphorylate that intermediate with the use of an ATP molecule again. So as a result, so far we've actually used two ATP molecules. And then as we continue further, we see that we actually now broken up these intermediates into two. So now there are two glyceraldehyde 3-phosphates, which, as it continues further down, it makes 1,3-bisphosphoglycerate with the help of glyceraldehyde 3-phosphate dehydrogenase in order to make one NADH for each one. So because there are two of these molecules, we actually make two NADH molecules. Now, as we continue further, we go from that intermediate into the formation of 3-phosphoglycerate with the help of phosphoglycerate kinase. This, in turn, results in the formation of ATP for each molecule, so two ATPs. And then as we go a little further down, with the conversion of phosphoenolpyruvate into pyruvate, and the help of pyruvate kinase, we make another ATP for each molecule as we remove that phosphate group. So as a result, we've gained 4 ATP molecules that we've made. We haven't lost any NADHs. However, in sum, we've made 2 NADH molecules, and we've made 2 net ATP molecules because of that loss that we had at the beginning of this pathway. So now, as we proceed on towards the oxidation of pyruvate, this is the conversion of pyruvate into acetyl-CoA. Overall, what we see going on that benefits ATP formation is the formation of NADH molecule. This happens in between at step 4 of this pathway after the formation of acetyl-CoA. So we have this byproduct, dihydrolipoamide, that needs to be recycled back into this pathway as lipoamide, which is an important coenzyme. This happens in step 4 as we're reforming this coenzyme. FAD will oxidize that right here, the intermediate, to form lipoamide. But then FAD also needs to be reoxidized back with the help of NAD+, and ultimately we get that NADH molecule. So as a result of this step, we've actually gained 2 more NADH molecules, bringing us to 4 NADH molecules and 2 net ATP molecules in total. So now we're moving on to citric acid cycle. So this also is happening twice, just like the oxidation of pyruvate from one glucose molecule. So as we go through this, we're forming a bunch of high energy products, which would be ATP, NADH, and FADH2. So to start off with, once we've made our isocitrate intermediate, it converts into alpha-ketoglutarate with the help of isocitrate dehydrogenase. Going through this step, we've made 1 NADH molecule for each cycle. So in total, we've made right there 2 NADH molecules, and as we proceed further, we go from alpha-ketoglutarate to succinyl-CoA. And this happens with the formation this enzyme alpha-ketoglutarate dehydrogenase complex. And here we have another 2 NADH molecules gained. And if we proceed further, we go from succinyl-CoA to succinate. With the help of succinyl-CoA synthetase, we now make an ATP molecule. So as a result, we now have 2 molecules of ATP gained from just this cycle. If we proceed further, we go from succinate to fumarate with the help of succinate dehydrogenase, and we've made an FADH2 molecule. So 2 of those. We continue now further from malate to oxaloacetate. With the help of malate dehydrogenase, we make another 2 molecules, bringing us to a total of 10 NADH molecules, 2 FADH2 molecules, and 4 ATP molecules. So now that we've made some of those important byproducts, we're going to take NADH and FADH2 and convert that into ATP. And we do this through the help of the electron transport chain and the ATP synthase. So as NADH goes through this electron transport chain, it can do so by entering in through complex 1. As a result, it can form 2.5 molecules of ATP. And this is only when we consider the NADHs that are formed in the mitochondrial matrix, so as a result of the citric acid cycle and the oxidation of pyruvate. However, NADH that is formed in the cytoplasm, such as glycolysis, these molecules will enter in at complex 2, much like FADH2 would, and it will only form 1.5 ATP because it doesn't pump out proton molecules through this complex, whereas in complex 1 it is pumping H+ molecules. So because of that decrease in protons being pumped out into the intermembrane space, we only form 1.5 ATP for that NADH. And of course, FADH2 as well only pumps 1.5 ATP as it goes through the ATP synthase. So now that we've gone over the conversion rates for these molecules, if we look at NADH from the mitochondrial matrix, there were 8 of those molecules, and with that conversion rate, we get 20 ATP molecules. With NADH, 2 of those being formed in the cytoplasm, we get 3 ATP molecules. With FADH2, there were 2 of those. We get 3 ATP molecules. And we need to consider some of the ATP that we formed in our earlier steps, which were 4. So in sum, we get 30 ATP molecules as we go through this process from 1 glucose molecule into this resulting 30 ATP.